Welcome, my name is Terry Soul, and this is Programming Chaos, a channel devoted to fun and interesting programming projects to help you hone your programming skills. Today's project is differential growth, which is this model that produces interesting, as you can see, organic looking forms, and it was recommended by one of our subscribers. The key to differential growth is we have a set of interconnected particles, often in a ring or a line, and there are a series of forces that both attract and repulse those particles from each other. And so before we begin the programming, we need to understand exactly what those forces are. So here I have a collection of particles, like we'd use for differential growth, and there are a number of forces that act on them. First, each particle is influenced by its neighbor. So I'll take, for example, this particle. If it is too close to its neighbors, then they repel each other. So we have repulsive forces pushing them apart. In contrast, if two neighbors are further apart, then they are attracted to each other. And so each particle is trying to maintain basically a constant distance from its neighbor. In addition, all particles within a certain radius repulse each other. So if, for example, we consider this particle, all of the particles within a certain radius are going to push it away. And that ends up creating typically a summed force that causes, in this case, the ring to expand. Although in some cases, if you consider this particle, its two neighbors are going to actually push it towards the center. And we'll see that behavior a lot in our differential growth models, some particles being pushed outward and some being pushed inward. Of course, we have balancing forces, so these may be pushing it in, but there may also be an attraction to them because they're neighbors, and both of those forces get applied. So we have repulsive forces for neighbors that are close together, attractive forces for neighbors that are further apart, and then this general, all particles are repulsed by all other ones within a radius. The final aspect of differential growth is if two neighboring particles get too far apart, we add a new one in between them. So for example, these two particles may be far enough apart that we add a new particle in the middle, and then these particles become that particle's neighbors. So that is the general idea. We need to implement all of those forces. We'll need to define a particle class, and then we'll need a list of particles to represent the whole set. So let's get to programming. So here I have my basic processing boilerplate. I'm going to be programming this in processing, which is a platform for really writing Java code. And as I said, the first thing I need is a particle class. There we go. And particles need a position and a velocity. And I'll represent both of those using the processing's p vector. And a p vector is just a vector with an x, a y, and a z component, although we won't be using the z component because we're sticking to 2 dimensions. And now I need a constructor for my particles. When we originally create our set of particles, we're going to want to arrange them in some particular way. I'll, for example, be arranging them in a circle, but because we want them arranged in a particular pattern, I'm going to pass the xy value, the location of the particle, to the constructor so it can put the particle at the appropriate location. And the initial velocity for the particles will be 0. And then the next thing I want is to be able to display the particles. And this is always helpful when you create a new class because it helps make sure that the class is behaving properly. To display a particle, all I'm going to do is display it at its xy position as a smallish circle. So that's the basics of our particle class, and now that we have it defined, we can create a set of them for the initial stage of our differential growth. I don't want to use an array of particles. Instead, I'm going to use an array list because that allows me to add more particles as we go. So this is an array list of particles, and I happen to call it a clump. Now that I have the array list, what I need to do is create all of my particles in the right location. So I'll do it as a ring and add them to the array list. There's creating the new array list. I'll start with 30 particles. And then to add the particles, I have to figure out where they're located around the ring. And to do that, I'm going to need to know the radius and the angle at which particle is located. So I'll start with a radius of 40, and I'm going to start with an angle of 0, but I'll tie that to which particle I'm placing. There we go. So the angle is really based on the value of I. I ranges from 0 to the number of particles, and I'm going to remap that from 0 to 2 pi. So that makes sure that my angle that I'm using to place the particles goes around 0 to 2 pi, evenly distributed. And the function for adding particles to, or adding items to an array list is just add. So I simply want to add here a new particle. And in order to construct that new particle, I have to give it the correct location. This is the X location. It's in the middle of the screen, so half the width, plus the radius that I want times the cosine of that angle. And then for the Y value, I'll do the same thing. There we go. So that will add all of my particles to my clump. And now I can go in and draw them and make sure that they're all in the right initial positions. Scroll up a little bit. So if you're not familiar with it, array lists have this nice functionality where we can simply say, for each particle P, for example, in clump, do something. And so this will loop over all of the particles in my array list and ask each of them to display themselves. So there we go. I have my ring of 30 particles all ready to go. And now I need to do two things. I need to write the insert function that will add extra particles, and I need to add the forces that are applied between the particles. So let's start with the insert function. After displaying the particles, I want to check to see if there's any that are far enough apart that I need to insert new ones. And I might want to have more than one clump of particles. So I'll tell the insert function which clump in particular to work on. So the idea is this function will go through this particular clump of particles and see if any new particles need to be inserted. To do that, I need to look at each particle, look at the distance to its neighbor. If that distance is great enough, then I need to put a new particle in between them. And so that means I'm going to have to go over each particle one at a time. In this case, I can't use this nice construction because I need to know numerically which particle I'm looking at. And that'll be a little clearer when I do the code. There we go. So I'm going to go over every particle in the clump by its index I. And so the first thing I need to do is grab the particle out of the array list so I can work with it. And for that, I'm using this get function that gets the ith item in the array list for me. And then I also need the next particle over. That's the next particle, so I can look at the distance between them. The only issue here is when I get to the last particle in the array, this will be out of bounds. And what I really want when I'm at the last particle is the next one over is the 0th particle. And so I can achieve that just by using a modulus operator. Now that I have those particles, I need to figure out the distance between them and, if necessary, insert a new particle in between. So let's do that. So I'll begin by creating a new p vector, which is going to represent the vector between those two particles. And I'll begin by copying the location of particle p1 into that difference vector. And then I'll subtract from that the position of the other particle. So I basically take the position of one particle, subtract the position of the other, and that in vector space gives me the vector between them. So I now have a vector going from one particle to the other. And what I want to do is look at the magnitude of that vector and determine if the magnitude is larger than my limit, and I need to insert a new vector in the middle, or a new particle in the middle. P vectors have a magnitude function, so this will tell me that the magnitude or the length of that vector. And if it's larger than the insert distance, then I need to insert a new particle. And I haven't defined the insert distance yet. I want to make that a parameter that I can change over time. The nice thing is I have this diff vector, which already goes from one particle to the other. So if I want to put a particle in the middle, I simply cut it in half and add that to my P vector. And that looks like this. So that's multiplying by 0.5, which cuts it in half. And then I can add a new particle to my clump using the same add that I did before. In this case, I need to add the particle at a particular location in the array list. So I need to add an extra parameter to the add function, which is the location that I want the particle to go into the array list in, which is I want it to go with the new I+1 position. And to be on the safe side, I need to do the modulus based on the size. And then I need to put in a new particle. And to put in a new particle, I need to give the location of that particle. And the location, as I said, is P plus half the difference. So that is the X component. And then for the Y value, I'll do the same thing. And that will put my particle in at the correct location. And the only thing I'm missing is my insert distance. So let's define that. And I'll arbitrarily set it at 15. And to see this work, what I want to do is start with many fewer particles. I'll just start with 4, and then we can see the new particles being inserted. I actually started with only 4 particles, but the other ones were inserted in between. So the insert's working. Now I can start worrying about applying the forces to the particles. So the way I'm going to do that is I'm going to ask each particle to update its velocity based on the other particles in the clump. So for each particle in the clump, I'm going to ask that particle to update itself given the location of all the other particles in the clump. The update function doesn't exist. Now we have to go and define that. So here's my update, and it is passed in the entire clump of particles to work with. This code is going to work fairly similarly to the insert in that what I need to know is the vector from all of the other particles to my current particle, the particle that's running the update. I have one vector to calculate that difference, so I can calculate the forces. And then I have another vector, which I'm calling forces, and I'll add each force to it as I calculate it. And then finally, it's useful to know the distance between the particles. And I'll just create another variable to store that. And so now I want to calculate the force between the current particle that's doing the update and every other particle in my clump. I just want to make sure that I'm not calculating the force of a particle on itself, because that would cause disastrous effects. And now, similar to insert, I'll figure out what this difference vector is between each pair of particles. This creates a vector from particle P to the current particle that's doing the update. And the distance is just the magnitude, that is to say, the length of that vector. And so now, if that distance is less than the repulsion distance, then they're going to apply a force on the current particle, pushing it away. And I'll need to define this. I want to make it a parameter because adjusting it can have interesting effects on the results. So the first thing I'll do is take that difference vector and normalize it so it's length 1, and then I'm going to rescale it based on the distance between the two particles. I'm multiplying it first by -1 because I want to make it a repulsive force, and then I'm dividing by the distance squared. So the further apart the particles are, the less force they apply to each other. You could instead do it just based on the distance instead of the distance squared, and I encourage you to play with that, or maybe even some other parameters for the force, but I found that this one works pretty well. And now that we've done that, we can just add this to the forces. So the idea is we're going to go through every single particle that is not this particle, check the distance, and if the distance is small enough, we'll calculate the force and add it to the total force. And then when we have the total force, we can add it to this particle's velocity. And if we want to be careful, we could add in an acceleration step in the middle. We have an acceleration vector which is equal to 0 for now. Then we copy the force into the acceleration, and we divide by the mass of the particle. But I'm treating all of my particles as having a mass of 1, so I'll just divide by 1. And then we add the acceleration to this particle's velocity. So I need to define the repulsion distance, and the other thing I need to do is apply the velocity to the particle's position. But I don't want to do that as part of this function. This function updates all of the velocities without moving any particles, and then I'll have another function that updates all of the positions. If I did both the velocity and the position as part of this function, it would throw off the model just a little bit because a particle would move before we calculated all of the other forces. And in fact, I can put that function in now. It just updates the position of a particle by adding that particle's velocity to its position. There's one more step that's useful here, and that is to reduce the velocity by some factor. You can think of this sort of like friction. It comes up in a lot of these sort of particle and force models. If you don't include a friction, the velocity keeps increasing and you get particles moving faster and faster, and that can sort of make this model very unstable. So adding this kind of frictional force is helpful. I need to put in my repulsion distance and actually need to call the update position function. And what I like to do is make the repulsion distance a factor of the insert distance, and times 5 seems to work pretty well. In addition to that, I need to apply my update position function. And it's the same idea for every particle P in my clump of particles, I have it update its own position. This puts in all of the forces that we need except for the neighboring forces. To get more control over the model, it's useful to put in another parameter for the forces. So I'm going to go back to my particle, and before I copy the forces into the acceleration, I'm going to multiply them by a parameter k. This is sort of like the spring constant if you're thinking of these forces as springs, or the gravitational constant if you're thinking of these forces as gravitational. And by controlling k, I have more control over how strong the forces are in general. And it turns out a pretty good value for k for the model that I'm working with here is about 20. I'm still missing the neighboring forces, but I have my repulsive force, and we can see how this works. So there we go. The particles are being pushed in part outwards, but some of them are being pushed inwards. And we keep inserting more and more particles, so we get this very complicated arrangement of lots and lots of particles. It doesn't look exactly like our differential growth for two reasons. One, I'm drawing the particles, not the lines between them, so we should add that. And two, I don't have the neighboring forces yet. So let's begin by drawing in the lines instead of the particles. So I'm going to comment out the part that is displaying the particles themselves, and instead I'm going to draw lines between them. And for that, I need to know the ith particle and the ith plus 1 particle, so I'm going to have to use a for loop with an actual I in there. So I'll get the ith particle, and then I'll get the ith plus 1 particle, using my modulus to make sure that I don't go past the end of the array and instead wrap back to particle number 0. And I'll put in a stroke color for now. And then I just need to draw a line between those two particles' positions. So that will draw a line between each pair of particles. Again, a very fancy, interesting looking shape. I'm not redrawing the background, so you get to see all the lines. If I put in the background, Now you can see the shape growing and expanding, and this is kind of like a standard differential growth, but it's a lot more jagged because we only have the repulsive force. So the next thing I want to do is put in the attractive forces. And I'm going to make that part of the update function. But in order to do that, I need another parameter. The issue here is when we look at the neighbors, the particle has to know which index it is. So if I'm updating particle 7, it needs to know that it's particle 7 so it can look at its neighbors, particle 6 and particle 8. And so that's going to require not only changing the update function a little bit, I also need to switch from this version of the for loop to the for loop that actually uses an I for the counting. So let me get rid of this and use the other version. And now I need to get the particle P. So I'm getting my particle P, which is the ith particle, and now I can ask P to update itself, but I can also tell it which number it is in the clump so it can find its neighbors. So for my update, I can add this second parameter n that I'm going to use to allow this particle to find its neighbors. And I want to do this after calculating the repulsive forces, but before applying the acceleration. So the number of the neighbor is the n+1 particle, again using the modulus of the clump size in case I have to wrap around. And then I'll get that neighboring particle. And now I just have to calculate the vector between them and check whether or not that distance is small enough that they should be repelling each other or attracting each other. So again, I copy the position of that temporary particle, which is the neighbor, and I subtract the position of the current particle, and the difference between them is the magnitude of that difference. And now that I have the distance, I'm going to normalize my vector and again divide it by the distance squared. So that's going to be the force that I apply. It's based on 1 over the distance squared between them. The only question is, should it be an attractive force or a repulsive force? And here's how I handle that. If the distance between them is less than half of the insertion distance, then I take that force that I just calculated and multiply it by -1. So if they're too close together, it's a repulsive force, the -1. If they're far enough apart, it remains an attractive force. And now I can simply add that into my overall set of forces. This applies a force from the +1 neighbor, the neighbor on the right, if you will. And I need to do the same exact thing for the neighbor on the left, and I'm going to be a little lazy here and just cut and paste this code. In this case, I don't need to redefine the neighbor, so I'll get rid of the int, but I do want to subtract 1. And if I subtract 1, I can't just do a modulus. I have to add the size of the clump and then take the modulus. So this will successfully wrap around the other way if necessary. And then similarly, temp already exists, so I don't have to declare it as a new variable. So now I'm calculating the forces based on the two neighbors. If we run this, we get a much more traditional looking differential growth pattern with the nice sort of smooth outlines. So it's worth pointing out that we have a bunch of parameters here that we can play with: the insert distance, the repulsion distance, the factor K, which is how strong the forces are. One of the things you may notice is that if you make some changes, it will throw the model off, at least until you adjust the parameters. So for example, if I make the insert distance very small, you get that sort of hideous spiky behavior. And what's happening there is we're getting two particles that are so close together, they're generating enormous forces and shooting way far off into the distance. And we can adjust that by reducing the amount of force we're applying, that our K constant here. And so now we're inserting a lot more particles close together, but because we're using a lower amount of force, the model doesn't become unstable. And so often you'll need to do that. As you adjust one parameter, you might need to adjust another parameter to make the model stable. A couple of other things we can do, and I will put these parameters back to what they were before, is we can add a little bit of initial noise to get more variation in our model. So right now, if I were to run this repeatedly, it wouldn't be obvious, but we'd get exactly the same pattern because there's no randomness in here. So there are different places to add randomness. I like to do it by putting it in as part of the radius. This adds just a bit of random noise to the initial particle positions, and it means that every time I run the program, I'll get a different looking system. And I'm starting with only 4 particles, and then it fills in a lot between them, so I could also start with a few more particles here. This notion that by putting in a little bit of randomness, I get very different patterns is an important one. And in order to illustrate it, I have a little bit of code here I'll run that actually creates 2 clumps simultaneously. There we go. So this is actually 2 clumps, but notice what happens as they start to expand, they expand in completely different ways. And the only difference between them was that little bit of noise where they started. This is one of the hallmarks of chaos. And it's what's known as sensitive dependence on the initial conditions. So the initial conditions here are almost identical, but they're slightly different due to that random noise, and yet it leads to completely different looking patterns. So let me run this again, and you can pay sort of careful attention. Initially, they're so close together that you can't even tell it's 2 clumps. As they grow, those very little differences in the radius, they actually grow exponentially, and so we get completely different outcomes. This shows that this is a chaotic system. It has a sensitive dependence on those initial conditions. Teeny variations initially create huge variations at the end. The last thing I want to do is make all of this prettier. So the way to do that is to come in and change how we're drawing the colors. I'm doing all of mine with a hue of 0, which is red. Instead, I'm going to set the hue so that it changes over time based on the frame count. And I'm going to do a modulus 360, so as we go around the color wheel, we come back to the beginning. And then I'm going to get rid of the background so that we can see each color as it's drawn. So if I run that, we get this sort of nice rainbow effect. We can make that even a little more impressive by adding transparency, and let's set the initial background to 0, so I have a black background, and then I'm going to come up and increase the initial number of particles to say 30. There we go. So now we get this semi-transparent form, but as it builds up, it keeps adding layers and layers. So it gives this sort of beautiful kind of neon 3D appearance. And you can play around a lot with factors like how many particles do we start with, how much transparency do you use the frame count, or maybe a multiplicative factor of the frame count. So let me show that very briefly. I could put in, instead of the frame count, maybe 0.5, and so now it doesn't update the colors quite as rapidly. And you'll see the same color for longer before it switches colors. The rainbow effect is a little less intense. So there's something to play with. You can play with the amount of transparency, the initial number of particles, the initial radius, or even the initial shape. So you can get very interesting effects by, instead of using a circle to begin with, a line or an arc or all sorts of different shapes. And of course, we can get more or less dense structures by changing all of these parameters. So lots of variations to play with. If you get anything really cool, please put a link in the comments below. Thank you.